So I'm going to talk about statistical analysis of network data. So first, here's like a little bit about me. If anybody can figure out where this picture was taken, feel free to just shout it out. I'm a senior data scientist. I have 8 years of industry experience as a data scientist, mostly on the statistics end of things, and a master's in it. So my formal background is very much in statistics, and you can scan this QR code and add me on LinkedIn if you want. So I'm going to jump right in and talk about the guiding example of this presentation, which is the ad health problem. So the ad health network is this network that was used as part of a big study in the 90s. It contains a lot of students, it contains many communities, and we're going to focus on one of them. So the survey, the ad health survey, asks a student to say, okay, who are your top 5 closest friends? And then ranks the levels of friendship. And then also tracks information about each student, so like their sex, race, grade level, and school. We're not going to deal with the rankings in this presentation. So the key guiding question of interest here is what factors influence the probability that a student considers another student to be their friend? And in network terms, this is probability of features leading to edge formation. So in a standard like statistical context, if we're just talking about like, Stats 101 or Grad Stats 101, we could, how do you model probabilities? Well, you use logistic regression. So, you build a model, it gives you the log odds of whatever the thing you're trying to predict is, whether that's, like fraud or something. And we do this by taking our data set and distilling it to essential generative features so that we capture the process that generated the data in a few statistics. So here's like, Fisher's iris data, it's pretty common. The idea here is, logistic regression, what does the data look like? It looks like the data in most other contexts. You have rows and columns, and you have independent separate observations. So, these are all separate flowers. Knowing about one of them doesn't tell me about the others. And when I say essential generative features in logistic regression, it's just the betas. So we're saying we can totally talk about the probability that a flower is a species using these 3 betas, provided our key assumptions like independence are met. So what happens if it's not? Then really bad things happen. The book I used to guide this analysis, has a quote. It goes on for pages. In a nutshell, we start concluding that relationships that don't actually exist are there, and that's really, really bad. In general, there are a lot of ways to handle lack of independence, assuming we know why it's violated. So like time series, is used for forecasting. There's multi-level modeling when you have hierarchical data, but what if we don't, right? Like what if we don't know what's leading to this violation of independence? Like we can't write it out. Well, now we're on statistical analysis of network data. So I'm not going to read directly off the slide, but the idea is networks are really complicated, and we need to take that complicatedness and turn it into something we can write down. And do you think we could like stick a logistic regression on this? Like this is the exact network that's our guiding example from the ad health, like the student friendship network. Like this is hard. What's going on? So instead of logistic regression, I'm going to talk about the exponential random graph model, or ERGM framework. So the idea here is instead of having like, probability distribution on like nice independent data points, instead we have a probability distribution that spits out networks. And in general, what we do is instead of treating it as, how a whole data set, we have a network like the one in the previous slide, and we treat it as one observation from a distribution of networks. And like logistic regression, we want to take this network and distill it to essential generative features that capture the process that made it. So this is the likelihood function. I'm not going to read off all the math, but in general, what this is saying is we have a bunch of network summary statistics. We have the network that we're curious about. And what we want to do is say, okay, how likely is it that we get this network compared to any other network that is generated with the same summary statistics, with the same number of vertices? So, if we have 10 students, the set of all networks is everything from 10 vertices with no edges connecting any of them, like nobody's friends with each other, to totally connected, meaning everybody lists everybody else as a friend. So there's some assumptions, they're very similar to those in linear regression or logistic regression. And there's the whole question of like, what the heck is a network statistic? So, in general, we talk about like a statistical distribution. You have the mean, you have the standard deviation, you have the kurtosis, you have other stuff. Is that what we're talking about here? And the answer is no. We have specific statistics that answer particular questions about a network. And there's hundreds of these. So I apologize for the font size. I didn't realize this TV was going to be that tiny, but in general, there's two categories, exogenous and endogenous. Exogenous features are kind of like those in any statistical analysis. Like they're things that happen outside the network. They don't deal with the adjacencies. So that's things like the student's sex, race, and grade level. And then we take those and turn them into statistics on like the whole graph. So for example, like our number of times in which two students who are friends are the same race. Or node mix, which is basically Cartesian product of like, okay, like our Latino students friends with like Middle Eastern students, and then for every possible pairing. And then we can look at things like grade level difference. So how far apart are students, if students are friends, how far apart are they in grade level? And then we can start answering some questions later on. There's also endogenous features. So this is the big benefit of the ERGM, of this graph framework. This is the killer feature, is we can talk about endogenous features, which are things that describe the network structure itself. Now this is fun. So network-specific things here are, we can talk about popularity. So you'll notice this student in the top left bubble has a bunch of arrows going in, meaning a lot of people say they're friends with them. There's sociality, which is, okay, this person says they have a lot of outgoing friends, like they're friends with a lot of people. There's reciprocity, so like, okay, this person, Alice says she's friends with Bob, does Bob say she's friends with Alice? If that's the case, then we have, both edges of the directed network pointed at each other. And transitivity, which is basically if I say I'm friends with you, you say you're friends with Dave, do I also say I'm friends with Dave? And then we can turn these into statistics, similarly the exogenous ones, where we basically count like how many people are there that say they have 5 friends, or how many people are there where other people say they have 5 friends, or how many instances are there where you have pairs of students saying they're friends with each other. And what we want to do is use these to capture the graph. And I'm not going to go through the math, but you can convince yourself that this is essentially what I just said in words. So let's fit an ERGM to this student friendship network data and then use that to answer some interesting questions. So for example, there's homophily, which is our friendships are more likely to form among students who are of the same race or the same sex. Or we can also look about like, are students who are farther apart in grade level less likely to be friends than students who are closer together in grade level? We can look at reciprocity. So we hypothesize that if there's a lot of people saying they're friends with each other and that's being returned, that new friendships in the network are likely. And then transitivity, so essentially the more friendship triangles there are, the more likely it is for new friendships to form. So the process of training one of these is kind of similar to training any other regression. What we do is, the first thing we do is train a null model that's basically just like mean number of edges. And you can think of that as like an intercept model in statistics. And I did this in R because when I came up with this presentation idea, I thought there was an ERGM package in Python. I didn't want to reinvent the wheel and do this all in like PyMC, so I did it in R. I apologize. And we work with a subset because otherwise this would take a while to fit. We fit the model. This is the bare bones model, and what this essentially is saying that edge formation in the graph is not random. And you'll also notice this looks a lot like logistic regression, which makes sense because we haven't started adding anything graph related yet. So the first thing we're going to do to this edges model is we're going to stick in exogenous features. So we put node match race, node match sex, and abs diff grade, which is just saying, are 2 students the same race? Are 2 students the same sex? And what is the absolute, we take the absolute value of the difference level of the grade level in the student's grade. So essentially what we see here is, like, before we start looking at anything graph related, two students being the same sex makes a friendship more likely, and two students being, with each additional close togetherness in grade, we start seeing a big jump in the probability of a friendship appearing somewhere in the network. So now we can add mutual dyads, which is like that reciprocity thing. So the number of pairs in which, I say I'm friends with you, you say you're friends with me. And it looks like this. I'm not going to go through it because we're going to build on this more. And then this is the most expensive slide in the deck. We start adding triangles. We don't actually add triangles because we start running into combinatorial issues, overflow, all the fun numerical stuff that we don't like. So we use basically a modified version that decreases that number. And I also add a term for out degree, which is basically just the number of people that report having exactly one friend. And I cheated here because when I fit this, it indicated that we had to do that. So before we actually look at the results, do diagnostics, this is basically just to make sure that your model, all the assumptions are being met. I'm not going to go through all of these, but you can convince yourself that the diagnostics fit, and we can proceed. There's also Markov chain stuff I'm not showing here. So here's the final model. I'm going to go through the key questions of interest line by line. First of all, we're going to talk about mutuality, so that's the reciprocity. So basically, after controlling for everything else, so the number of edges, are the two students the same race, the same sex, this GWESP thing, which is basically something about triangles, we see that there's almost an increase in 4 in log odds with every additional reciprocal friendship pair, which this is good. It basically says, like, if kids are friends with each other and, I say I'm friends with you, you say you're friends with me, we're more likely to make more friends. We can look at this triangle thing. So when we add triangles, we also start seeing more friendships. And then also this out degree thing. It wasn't the question of interest, but when I fit the model, we definitely indicated we needed this. Essentially, if we have a lot of people that report having only a single friend, then we start seeing the log odds of like new friendships going down, which makes sense because it doesn't seem like they're trying to expand and meet a lot of new people. So with this framework, I'll briefly talk about the strengths and weaknesses. So the biggest benefit here is the ERGM is really the only framework that can take these endogenous graph properties into account. So like, the connectivity things that we've distilled from our summary statistics. We have specific questions about the graph, and we can turn those into statistics we put in the model and see, what's going on with like reciprocity or sociality. Like, we can quantify that. There's hundreds of these. There's a really easy framework I didn't get into for making new ones, and it's extremely conceptually similar to logistic regression. The biggest downside is like there's a lot of numerical issues with fitting these. I didn't want to get into it. If this was a 30-minute talk, I would, but this is a tricky problem. There's all kinds of literature around how to fix it. Training time can be slow. You can't take like temporality, so let's say like, I don't know, like pre-Cold War or post-Cold War networks or something, but there are frameworks for that and for taking like weighted graphs into account. And once again, unfortunately, there's no way to do this in Python as of today. There's a whole bunch of additional topics that are covered in the book that if I was doing a workshop on, I would talk about. And if you liked this and you want to keep in touch, I have my LinkedIn, and also I don't have a job right now, so if you want to hire me and you thought this was good, definitely add me, or if you just want to, like talk tech or stats or something, you can also talk to me. Thanks. Oh, hold on, I have questions. Jared, yes.
How do you account for multicellularity in exogenous or endogenous variables?
Basically just use common sense. So you should never put in multiple statistics that capture the exact same information. So don't put in like number of triangles and also like the weighted decayed version of triangles.
Yeah, so like for endogenous variables, they're basically transformations of exogenous variables.
So endogenous variables and exogenous are separate. So endogenous is more like categorical things or like things that basically exist outside the network. Yeah. Endogenous is specifically around like connectivity and like graph properties. So essentially, like, you're not transforming exogenous to endogenous. You're taking, like, exogenous and basically, like, taking the connectivity in the graph and turning it into a bunch of summary statistics, which are then the things that you interpret in the ERGM. Does that make sense?
Sure. I just thought it was pretty the archive was like there's like a function you call
Yes.
based off of things.
Once again, I didn't realize this was going to be so small from far away. Yes?
Yeah, so I guess, so the endogenous variables, they're like they're like you reason on the graph and come up with,
Yeah. So it's more like if you have particular questions, it's about like these things, which pop up a lot in the social sciences, then you generally like, okay, we're interested in reciprocity, therefore we need to find a statistic that captures that.
right.
Or, oh, we're interested in like transitivity, so there are statistics for that. And there's a million of these. You could talk about like, okay, what's the probability of edges not forming? You can talk about like, you know, like non-connectivity. But yeah, you generally need some level of domain knowledge to figure out like, what do I even start to include? Yes?
You talked about independence. How do you establish that your data is independent?
That's a rabbit hole. Generally, it's just based on how did you collect the data. So for example, if the data was collected, let's say you have data collected from 15 classrooms in a school, and then let's say 15 classrooms each in 50 schools, you generally just know based on domain knowledge that like people who are in the same class are going to have very similar numbers. Does that make sense? Thanks.
All right.
All right.
Send the wrap.
Thank you.
Great, thank you very much.